Hello everyone, myself Dr. Ranjith Kumar Gatla, working as an Associate Professor in the Department of Electrical and Electronics Engineering at Institute of Aeronautical Engineering. So in today's class, we are going to discuss or we are going to solve some numerical problems based on the topic which is electromagnetic induction. So in the previous class, we have discussed what is electromagnetic induction, and in that we have discussed what is electromagnetic field and what are the Faraday's laws. So like these are the things that we have, and what is the inductor, okay, what is inductance, like these concepts that we have already discussed in the previous class, and based on those concepts here, we are trying to solve some numerical problems, right? Because it is very important, because the numerical problems, because when we are while solving the numerical problems, we will just recall the concepts which we are discussed in the previous classes, right? So to get, I mean, practically we are just applying those concepts here to find the variables. Or here we can also understand the relation between the various parameters related to the electromagnetic field, right? So coming to the first problem, here a conductor having a 300 mm long moves at a uniform speed of 4 meters per second at right angle to a uniform magnetic field of flux density 1.25, determine the current flowing in the conductor when its ends are open circuited, and the second case is its ends are connected to a load of 20 ohms resistance. So before going to solve this problem here what they are asking us to find, determine the current flowing through the conductor when its ends are open circuited. So which means if the ends are open circuited, of course the current flowing through that particular circuit will be zero, but there will be a potential difference across those two terminals. So which means we have to calculate the potential difference or the EMF induced across those two terminals. Then the second case, if the ends are connected to a load of 20 ohms resistor, which means they are just closed that particular circuit by connecting a load of 20 ohms resistance, which means now the current flowing through that particular circuit. So which means here we have to find what is the potential difference across those two terminals, or the EMF across those two terminals, and as well as EMF means electromotive force, and as well as the current flowing through that particular circuit, right? So which means then what is the relation here? It is E is equal to, okay, the induced EMF across the coil, E is equal to B into L into V, which means here you are moving the coil, okay, in between the field, okay. Of course, how you are producing the field, let us consider you are having just two magnets, one is having the north pole, another one is having the south pole. Of course, there should be a the flux density or the magnetic field density in between these two plates. Then when you place a conductor, okay, so here the conductor the conductor is moving with a velocity, okay, so let us consider V, okay, then there will be a EMF induced across this conductor or in the coil, okay. So then what is the EMF induced across the coil, and what is the current flowing through that coil, that we need to calculate. So further here E is equal to B into L into V. So here B is the flux density. Of course, we know that the flux density measured in terms of Tesla are the units for the flux density, and here L is the length of the conductor which we are placed in that particular magnetic field, and of course that is measured in terms of meters. And then here V is the conductor velocity which we have placed, okay, because here as we know any one of the either conductor or the field, okay, so any one of these two, okay, must be having in a motion, okay. So otherwise if both are at the stationary, then we won't get any magnetic field. So that's why here the field is stationary and the conductor is moving, so that's why an EMF is induced across the terminals of that particular conductor. So these concepts we have already discussed, okay. Then just for the recall purpose, okay, I'm just again trying to discuss in a brief. So just substitute here B that they have given. B is equal to what is the value of the B here? It is 1.25 Tesla, and L, the length here it is where is the length? Yeah, 300 mm. Of course, we need to convert again into the meters. And V, the velocity here it is 4 meters per second. Of course, that is as per the units. Then substitute all these values in this particular equation. Then you will get the EMF induced are across the particular coil, so which is equal to 1.5 volts. Then the another equation, as we know, because E is equal to I into R, okay, that they have given R. So from this you can find I is equal to E by R. So substitute the value of E here it is, because just now we have calculated 1.5 by 20. Then you will get the current flowing through that particular conductor, which is equal to 75 milliamperes. So this is how we need to find. Then the second problem, okay, of course based on the same equation. At what velocity must a conductor 75 mm long cut a magnetic field or the flux density of 0.6 Tesla if an EMF of 9 volts is to be induced in it? Okay, then assume the conductor and the field and the direction of the motion are mutually perpendicular. Of course, because it must be the mutually perpendicular. Okay, these concepts already we have discussed. Okay, then which means again the same equation. So E is equal to B into L into V. So here, of course, everything that they have given, so the velocity. So we must find the velocity. V is equal to E by B into L. So substitute the value of E, which is equal to 9 volts, and B, which is equal to 0.6 Tesla, and L is equal to 75 mm. So which means 75 into 10 to the power of minus 3 meters. And substitute all these values and simplify. Then you will get the velocity here. It will be 200 meters per second. So this is how we need to find. Then the third problem here it is, determine the EMF induced in a coil of 200 turns when there is a change of flux of 25 milliwebers linking with it in 50 milliseconds. Okay, so which means here we need to find the EMF. Of course, because there is because there are many relations, there are many parameters that can affect the EMF. In the previous case, what we have discussed, okay, the EMF can be affected by the flux density as well as the length of the conductor as well as the velocity of the conductor. So in this case, now we are going to discuss some more parameters. Okay, so just not only the length and the flux density and the velocity of the conductor. So it will also, okay, so depends on the number of turns and the rate of change of flux. Okay, the number of turns and the rate of change of flux, right? So that's why here what they have given in the equation, the coil has 200 turns. So which means the number of turns N is equal to 200, and the change of flux, okay, the change of flux here it is, which means d phi by dt, which is equal to here 25 by 50. Okay, both are milli, so that's why we no need to take care. Okay, so 25 into 10 to the power of minus 3 by 15 to 10 to the power of minus 3. So then substitute here, or in another words, okay, in another words, the EMF induced in that particular coil is also depends on the self-inductance of that particular coil and the rate of change of current that is flowing through that coil. Of course, because here the current is directly proportional to the flux, which means the rate of change of current is directly proportional to the rate of change of flux. Okay, so that is why here we can just we can also define the equation for the EMF E is equal to minus L into di by dt. So by using these two equations, now we are going to solve this particular problem. So here we have used the first equation. So substitute the value of N, which is 200, and the d phi by dt, which is 25 by 50. Okay, then you will get the induced EMF E is equal to minus 100 volts. So I think again I don't need to explain why here we have included the negative sign, because according to the Lenz law. Then coming to the fourth problem, calculate the EMF induced in a coil of inductance 12 henries by a current changing at a rate of 4 amperes per second. The same way, because just now we have calculated in this case, now we are going to use the second equation, which is EMF E is equal to minus L into di by dt. So here L is 12, okay, L is 12 and di by dt is 4. Just substitute, then you will get here it is minus 48 volts. So which is the EMF induced in that particular coil. So this is how we can find or we can solve this particular problem. Next, another. So here an 8 henries inductor has a current of 3 amperes flowing through it. How much energy is stored in the magnetic field of the conductor? Of course, again the same equation. So here L is equal to not L, here E is equal to minus L into di by dt. Then substitute the values here, minus L. So here, of course, L value here it is 8 into here di by dt. Has a current of 3 amperes flowing through it. Okay. So which means 3 amperes. Okay. Then substitute in here. Then you will get, sorry, here it is energy stored. Okay. Not the EMF, right? This is another concept. Okay. Sorry. So here the energy stored, okay, there is another case, okay, because as we know, the inductor, okay, will store the energy in the form of magnetic field. Right. Then what is the amount of energy that stores by the inductor in the form of magnetic field? So that is W is equal to 1 by 2 into L into I square. So here L is inductor and I is the current flowing through that particular coil, right? And L is the self-inductance of that particular coil. So then just substitute in this equation, W is equal to 1 by 2 into here L is, where is L? L here it is 8 and I square here it is 3 square. Then simplify this, then you will get here the answer for energy stored in this particular, conductor here it is 36 joules. Of course, we know the units for the energy here it is joules. So this is the problem 5. Next, coming to the problem 6. Calculate the coil inductance when a current of 4 amperes in a coil of 800 turns produces a flux of 5 milliwebers linking the coil. So which means now we need to find the coil inductance, right? So as we know, the inductance is also, we can define the, this is another equation. I'm just trying to recall all the equations because these concepts already we have discussed in the previous classes. Then here N into phi by I. So here the inductance of the coil is directly proportional to the number of turns of that particular coil and the flux produced by that particular coil, and inversely proportional to the current flowing through that particular coil. So that we can make it as in another words, okay, so because here N is equal to constant, okay, or in another words, we can write this one as a L is directly proportional to phi by I. So which means L is directly proportional to phi and L is inversely proportional to I. So if you just remove this proportionality, then we can make it as a L is equal to N into phi by I. So here N is the number of turns which is constant, right? Then substitute all these values here because we know the value of N, that is 800 turns that they have given, and the phi, which is the flux produced, the flux linking with that particular coil is 5 milliwebers, so which means 5 into 10 to the power of minus 3. And the current here it is 4 amperes. You substitute all these values, then you will get finally the inductance of the particular coil, which is equal to 1 Henry. Right? Then coming to the another problem. So here just we need to understand the concept, and based on the given parameters, we need to recall the equations which is related to these all parameters so that we can easily solve these problems. Then the 7th problem here it is a flux of 25 milliwebers links with a 1500 turns coil when a current 3 amperes passes through the coil. Calculate the inductance of the coil. Of course, simply just inductance means L is equal to which is equal to N into phi by I. So all the parameters that they have given, we can find the L value by using this particular equation. Then the energy stored in the magnetic field, okay, that just now we have calculated F is equal to 1 by 2 into L into I square, right? And the average EMF induced in the coil falls to 0 in 150 milliseconds. And then we have to find the average induced EMF E also. So which means whatever the equations that we have discussed, we need to use all these equations here to find all these 3 parameters. So first let us find the first parameters here, which is equal to the inductance L. So L is equal to N into phi by I. So substitute the N value, N is equal to 1500 turns and phi is equal to 25 into 10 to the power of minus 3, because here that they have given 25 milliwebers. So we need to convert into the webers, and I is equal to 3 amperes. Then by simplifying this particular equation, then you will get the inductance L is equal to 12.5 amperes. Then substitute this one into this equation, which is equal to W, the energy stored in that particular coil. W is equal to 1 by 2 into Li square of Li square. Then again, just now we have calculated the value of L, which is equal to 12.5 Henries, and substitute this 12.5 Henries in this L value, and I value as we know already, which is 3. So substitute these two values in this particular equation, then you will get finally the energy stored in that particular coil, which is equal to 56.25 joules. Next, the third one, which is the induced EMF. So induced EMF, which is equal to minus L into di by dt. Okay, or minus what is that, N into d phi by dt. But anyway, here we don't know what is d phi by dt, and we don't know the number of turns, or of course 500 turns that they have given. So of course, instead of that, we have used this particular equation, E is equal to minus L into di by dt. Then substitute the value of L and di by dt value, then you will get, because di means the difference between the current, here it is 3 and 0, let us consider. So 3 by here, which is 150 milliseconds, so 150 into 10 to the power of minus 3. Then by simplifying this equation, then you will get the average EMF induced, okay, is minus 250 volts. So this is how we can simplify or solve the numerical problems based on the electromagnetic induction. Then coming to the eighth problem. And a 750 turns coil of inductance 3 Henries carries a current 2 amperes. Calculate the flux linking the coil and EMF induced in the coil when the current collapses to 0 in 20 milliseconds. Of course, by using again the same equations. Okay, so first of all, we have to find the inductance L is equal to N into phi by I. Okay, so from that, because already they have given the inductance, which is 3 Henries. So, but we don't know the flux that we need to find. So, from this equation, we can find the flux. So, flux F is equal to, or phi is equal to L into I by N. Then substitute all these values. Here, L is equal to 3 Henries and I is equal to 2 amperes and N is 750 turns. Then substitute. Then you will get the flux phi is equal to 8 milliwebers. Then from that, what we need to find? We have to find the EMF. Okay. So the EMF E is equal to minus L into di by dt. Then substitute the value. Here L is equal to 3 and again di by dt 2 minus 0 by dt. Here it is 20 milliseconds, which means 20 into 10 to the power of minus 3. Then by simplifying this, then you will get the induced EMF E is equal to minus 300 volts. Right. So this is how. And then of course, there is another alternative method also, because as I told you, there are two equations for the induced EMF. One is in terms of I, another one is in terms of phi. So here in terms of I, E is equal to minus L into di by dt, and in terms of phi, E is equal to minus N into d phi by dt, because here we know the value of N also, which is equal to 750 turns. So you just substitute N into d phi by dt, so that is equal to 750, and phi just now we have calculated, which is 8 milliwebers. And by t here again 20 milliseconds, if you substitute all these values in this equation, E is equal to minus N into d phi by dt, then you will get the value, again here it is minus 300 volts, which means to find the induced EMF, you can use any one of the equation. In the previous problem also, okay, you can use, instead of this, you can also use E is equal to minus N into d phi by dt also, because we know the phi value also. Let me see here whether do we know the phi. Yeah, the flux value also we know. Okay, just substitute all these values here. Minus N is equal to 15 minus 1500 into 25 into 10 to the power of minus 3 by here 150 into 10 to the power of minus 3. If you simplify, then you will get again minus 250 volts. Right. So which means we can use any one of the equation based on the available parameters. Right. Then coming to the ninth problem, calculate the mutual inductance between the two coils when a current changing at 200 amperes per second in one coil induced an EMF of 1.5 volts in each other. So which means now here there is another concept called mutual inductance. Right. So when there are two coils, then the EMF produced in the second coil, because of the current flowing through the first coil, okay, then here the EMF induced across the second coil, which is equal to minus M into di by dt. Right. So here we know the mutual inductance that they have given. Okay, no, they are asking us to find the mutual inductance. Then from this we have to find the M, because here they have given E2, which is equal to 1.5 volts, and what is that? Change in current di by dt, which is equal to 200 amperes per second. Okay, so just substitute these two values here, then you will get the value of M. So then the value of the M here, it is equal to the mutual inductance is equal to 7.5 millihenries. So this is how we can find the concept of mutual inductance. So we just recall, right? And again, The last problem for this today's session here is two coils have a mutual inductance of 0.2 henries if the current in one coil is changes from 10 amperes to 4 amperes in 10 milliseconds, and calculate the average induced EMF in the second coil and the change of flux linked with the second coil if it is wound with 500 turns. Then the same equation, okay, by using this equation we can find, and by using this equation also we can find. Because first of all we need to find the EMF. Okay, so the EMF here it is minus 20 volts, and just by using that EMF we need to find the change in flux. Okay, so the change in flux here it is this one. Okay, the change in flux here it is 2.4 milliwebers. So this is how we can solve the numerical problems from the electromagnetic induction principle, right? So thank you. So in the next class we will discuss the next problem. The another concept.
Like, share and subscribe. Hit the bell icon for more updates.